Let's take a look at a function defined by a graph. Remember that if f of x is equal to y, the function f inverse, which undoes the function f, would take the y value from the previous example as its input and give the x value from the previous example as its output. So if we want to find f inverse of 4, but the graph we're looking at represents the function f, then we know that what we're given is really a y value, and what our answer is going to be is really an x value. So I'm going to look for a function, or sorry, a point on this graph with y coordinate 4, which I can see occurs right here at the point 2, 4. So where y is 4, it looks like x is equal to 2. So one thing I can do with a graph is just evaluate a function or evaluate an inverse function for particular inputs. But another thing I can do is draw a graph of the inverse. It's going to be helpful in this case to label the coordinates of each of these points. This first point is at -4, -3. This second point is at -3, 1. This third point is at 1, 2, and we've already labeled the point 2, 4. With a function that's defined numerically, we learned that we could just swap the rows of x and y so that we're exchanging input values for output values. The same thing works with a graph. We're going to now just swap the coordinates for x and y. We're not changing signs of anything. We're just taking the numbers, picking them up, and putting them down exactly as they are in the other position. So for example, the point -4, -3 becomes -3, -4. And the point -3, 1 becomes 1, -3. The point 1, 2 becomes 2, 1, and the last point 2, 4 becomes 4, 2. Now if I connect these with line segments, I get a graph of the inverse function f inverse. And again, if I'm evaluating a point from the inverse function, if I'm looking at this graph and I'm asked to find f inverse of 4, I now read it in the forward direction, right? As if 4 is now my input variable x, and I'm trying to find an output variable y. So I still get f inverse of 4 equals 2. So if I'm asked a question about an inverse function and the graph I'm looking at is the original function, I read it backwards. If I'm asked a question about an inverse function but I've already found the inverse, then I'm just reading that function in a forward direction. Another way to think about the inverse of a function defined by a graph is that it is a reflection about the line y equals x. So here's what that looks like. If I draw in a nice dashed or very thin line here, I'll draw it in green, with slope 1 and passing through the origin. This is the line y equals x. To reflect each of these points about that line, what I would have to do is locate the point, count the steps going directly toward the line, and then keep going that same number of steps on the other side, so it's as if this line is acting as a mirror. Take this point here, I can kind of measure the distance going toward the line, and then try to keep going that same distance again on the other side to get a point on the other side of the line until I get all the points that would connect into the graph of the inverse. So the process we followed of swapping coordinates did this for us automatically. So where this first graph here is f, this second graph, which I just drew, would be f inverse. This is not as easy a process as some of the other things we can do, but it's a good thing to keep in mind because it's an excellent check. At the end of drawing a graph of an inverse function, it's a great idea to just dash in the line y equals x and see if it looks like that line acts as a mirror between your original graph and your inverse graph. Now, in the previous example, we were able to get a really good graph of an inverse just by swapping coordinates of points. That's not always possible. For example, here, I can identify a few good points to swap the coordinates of. I can see 0, -1. I can see 1, 1. I can see 2, 4. Anything else I take is going to have fractional values, and I would need to sample a lot of points in order to really get this shape. So I'll go ahead and swap the coordinates on those just to get this started, but we'll see that that's not quite enough to draw the whole graph. We'll need some more tricks. So 0, -1 becomes -1, 0. 1, 1 stays the same when I swap those coordinates, nothing changes. And 2, 4 becomes 4, 2. All right, so the y-intercept 0, 1 we see became the x-intercept. -1, 0. So what we really have going on here is not just coordinates of points swapping, but in fact all characteristics of the graph that were associated with the x value in the original function f are now associated with the y value in our new function f inverse. In particular, this asymptote has the equation y equals -2. So that's really a y characteristic. What I get on my inverse function is no change to the sign of the number at all, but instead of y we have x. So if the equation is now x equals -2, we see that that's in fact a vertical asymptote. So I'm going to dash in that line, or just draw it with a really thin line here. Maybe I'll just draw it a little bit thicker but with a lighter color so that we can see it better. I have a vertical asymptote at x equals -2. I want to emphasize we really didn't change from -2 to +2, right? We only changed from y to x. Now with just that feature, I can really see how this graph has got to look. I can connect these points up this way, but the graph has to approach the asymptote, and I know that it's going to have a similar shape to my original graph because of that reflection about the line y equals x. If I sketch in the line y equals x just as a little check here, and I lightly sketch in my original function, which looked like this. I can see that symmetry about the line y equals x, right? I can see that reflection happening where the original function crossed the line y equals x. That point is the same on both functions, but all of the other points are reflected across that line. All right, and finally we'll look at these and just from the graph determine the domain and range of each. Looking at our original function f, we can see that the domain appears to go off to -infinity on the left since we have this arrow on the graph, and +infinity on the right since we have an arrow going upward, to the right. We don't have a vertical asymptote that would cut it off anywhere, so we can assume that that also keeps going off to the right. So our domain appears to go from negative infinity to infinity, or we could just say all real numbers. The range looks like it has a lower bound of -2, which the graph never quite attains, so we're going to use an open bracket here at -2, and it goes up to positive infinity. Looking now at our inverse function, we can see that the domain this time has a lower bound of -2, and that is a value it never attains. So our domain is from -2 to infinity, and our range this time looks like it goes from negative infinity to positive infinity. So that's yet another x characteristic and y characteristic that have swapped, right? This range could also be written as the set of all real numbers, so that we can see the domain of the original function is the same as the range of the inverse function. And we can also see that the domain, or rather the range of our original function, is equal to the domain of our inverse function. So all x and y characteristics, or rather all input and output variable characteristics, swap when you go between the original function and its inverse.